Good afternoon, everyone. Imagine this. It's Monday morning, you roll out of bed and get ready for work. And your employer is Abyssal Depths Diving, a mid-sized engineering company that does undersea cable maintenance. Surprisingly topical these days. And your team is responsible for a Java service that provides an API to access undersea dive sites that need to be cable maintenance, essentially. It's built with Java and Quarkus. And the system architecture looks roughly like this. It's pretty typical of a modern app. There's some Kubernetes, there's a bunch of different services in different programming languages. Bit of a mess, but probably fairly indicative of how we do things these days. We can see our service over to the side here, as well as some other things in Go, Rust, and Python, and so on. You open your fancy new M4 Mac, and you check your email. And you already have email from John, the platform architect, who in this photo is enjoying a lovely holiday in the sea. He says, "Hello, we would like everyone in the team to add the platform tagging library to all of the services this week." And you sigh, once again confronted by one of John's various cross-cutting initiatives. But in this case, it's pretty straightforward. John has given us a new component, the curiously named Horror API, and it's basically a mechanism to wrap up a bunch of standard headers that we want on the responses of all of our REST APIs everywhere. But as we can see, it's packaged up into a nice Java library. It's nothing too heinous. What could possibly go wrong? We've even got a Maven dependency. It's a snapshot, which is maybe a bit of a smell, but we'll let that one slide for the moment, John. So once we have this, we have a pretty standard configuration of things, right? We have our Dave's API, which is the Quarkus app up the top. We have the Horror API, which is the Java dependency we're adding, running on the JVM, hopefully on a fancy Mac. So we go and we try and add this to one of our REST endpoints. We have a Quarkus handler here. You don't need to read all the code, but the main thing is we have a normal tag library at the top. We build a helper to add tag headers to any response, and we use it for get all. We fire up Quarkus dev, hit our test endpoint, and are confronted immediately by this rather intense looking error. We can see at the top that we can't find the tag library, which is the part inside this API we're trying to use. And if we scroll dramatically across and then squint, we can find this, which is maybe a little bit helpful. livtag.so is not a Mark O file. Hi, I'm Scott. I'm from Datadog, or as most of my colleagues like to call it, Datadog. And welcome to the session today on high-level programming languages and how they relate to the Linux compiler suite underneath. And Java and other languages have given us a big level up as developers. We don't have to mostly care about these things, how Linux works, how the C runtime works. But every now and again, these gritty low-level details can leak up and impact us at times and in ways that we don't really enjoy and are probably rather inopportune. And this talk is about that. When these things happen, how we can avoid them happening, and some general strategies for dealing with them. Let's get stuck in. So if we Google, as we are prone to do, or go on Stack Overflow, we discover that Marco, the Mark object file format, is the file format used for executables, object files, shared libraries on the Mark kernel system. And this means macOS. We can also Google that and discover that. If we look up .so, we discover that that's typically associated with ELF, which is exactly the same thing, but for Linux. So if we go back to our error message, we can surmise that John, the platform architect, has given us a nice Java library and not mentioned that it wraps up a native library underneath. And then he's only given us the Linux library that we need for the native thing, so we can't run it on our Mac. And this might seem super obtuse to start with, like, why have you done this, John? And the trick is kind of the initial architecture diagram. We have all these different programming languages we have to support, or John's team has to support. And really the only reasonable way of doing that these days is to build a native library and then wrap it up with bindings for the actual languages that we want to use. So we'll let that one slide and we'll go on to trying and fixing this thing so it actually works for us. And on the right, we have the different files that are involved in the thing so far. We can see that we have taglibrary.java, which is going to be the Java wrapper for the native component, taglibrary.c, which is going to be the native component, a bit of build stuff, and then the output files at the bottom. So the actual Linux library and the jar that we want to package it all up into. And to fix this up, we're going to need to do a few things. We'll have to make a macOS variant of the library so that we can run it in dev mode. We'll have to modify the jar so that the Java wrapper actually picks up the library at runtime depending on whether it's running on a Mac or on Linux. And we'll need to fix the build, which will probably be the least pleasant part of the experience. But quickly, a brief aside into compilers, because this is something that we're going to have to play with. And on Linux and macOS these days, there are kind of two main compiler suites. There's GCC, which is the really old one, And there's LLVM, which is the fancy newer one that things like Rust use as the backend for their code generation. And in both compiler suites, in most compiler suites, you have compilers which take a piece of source code file by file and produce kind of like an intermediate representation of that. I've used a bad word, like they compile the individual files. And then you have a linker which takes all of those individual files compiled output and combines them into a shared library like we need today, or an executable. And a fun fact about LLVM is that it was built in a way so that you can use it as a drop-in replacement for GCC in many cases. And you can kind of imagine why. In the Linux community, there's this massive infrastructure built up around compiling things like the kernel that is arcane and complicated and has been built over decades. And by being command line compatible with GCC, you can easily use LLVM without having to change all of that. In fact, in the top screenshot here, we can see that if we have our fancy Mac and we ask it what version of GCC it has, it tells us that it's actually LLVM. On Linux, on the other hand, when you use GCC, you typically actually have GCC, although you can always install LLVM if you want to. So this is kind of a fun aside. We're going to use both compilers to make this thing work, but for most use cases, they're pretty interchangeable. And this is kind of what we're doing. We have the source files, we have at the very top, we have taglibrary.c, so the one that we actually want to compile. A couple of other ones that I've added to make the diagram a bit more interesting. And we want to run them through the compiler and produce object files. And object files are compiled, they're built for the machine code that you're targeting, but they're not useful yet. They reference symbols that exist somewhere, but they don't say how to get them. So for instance, main.c might call a function in taglibrary.c. It just says, I need to call this function, but it hasn't resolved it yet. Similarly, taglibrary.c might use printf, and it knows that it needs it, but it doesn't know how to get it. So we take these files, and we jam them through the linker, and we ask the linker to either produce us a shared library, if we want to use it in another application like we are today, or an executable if we also provide an entry point like main. And there are different arguments to get the two different variants. If we zoom dramatically across and compare this to Java, it's kind of same but different. We still have some source code, we run it through the Java compiler, but we end up with this intermediate representation. So it's being compiled, but it's compiled for an abstract virtual machine that nothing can actually run. We then jam that through the Java runtime, which does some interpretation, some compilation, and ultimately makes it run on the machine that you've executed it on. And this is what gives Java the nice advantages that avoid this whole complexity with C. You can build your application once and run it everywhere, famously. The Java runtime also lets us call native code over JNI. So as the tag library class, we can say, hey, we want to go and call this native function in this shared object. Please do it for us, Java. You generally don't have to do this so much unless you end up in situations like this, where you're reusing code across multiple languages, or you're using something like OpenSSL, where your Maven dependency is secretly hiding away this dependency from you, but you still have it. So jumping into the code itself in Helix, which is a great text editor in case no one has been using Helix yet, I encourage it. And we'll start off with taglibrary.java. This is kind of straightforward. This is the part that's wrapping up the native code. So we can see at the very top, we're saying, hey, we need to load taglibrary.so. And if somebody asks for it, try and do it. And this is what's causing the issue. We can't load that file. So pretty straightforward. We need to change it so that we load the file based on the platform we're on. So the Java starts up, it says, hey, I'm on a Mac. Let's load the -Darwin version. Darwin is the name of the Mac kernel. Hey, we're on Linux, let's load that. Hey, we're on Windows, go and buy another computer. So that part's good, that part's straightforward. Next, we need to see how the build actually works so that we can make the build run on Mac as well. And we can see we have this helpful build script that someone has written. And we start off by running docker build, passing it Linux as a platform. And then at the bottom, we pull a file out of that build container, which is the target library that we need for Linux. And we can include that in our jar. So we need to go a bit deeper, have a look at the build file. It's running a make file. Have a look at the make file and be immediately confronted by how unpleasant make files are. I mean, it's not as bad as Perl, but it's certainly going in that direction. But we don't need all of this. We just kind of need to see how this thing is actually building the code. And if we zip around a bit, we can see something that roughly reflects what we were talking about before with the different stages of compilation. We have two rules. We have one to compile the individual files, and we have a second rule to take the compiled files, the object set that we have, and link them into a shared library. So where we have obster :%.o, we're saying if you want to produce a .o file in the object directory, then you can take a .c file from the source directory and run this command on the next line to do so. The library step is exactly the same, except it's taking a list of all of the objects and saying, give me a shared library from this. This is still a little bit abstract, but if we go and look at what those variables evaluate to, we can see that CC is the GCC, so our compiler, and in CFlags we're saying we want a shared library, and we have this other argument fpic which makes it relocatable. It doesn't really matter, but you typically see these two together. So fundamentally, we could take this makefile and we could make it run on Mac as well. This would be a more normal thing to do, but I would rather convince you that it's not actually that hard to do the native compilation, so we'll make it a bit simpler. And you can imagine now that build native is running on our Mac. So when we do the first part, we've already talked about the Docker build. We're doing it inside a Docker container, pretending to be Linux on ARM64. This bit we've added is running natively, and we've basically just taken all the bits from the makefile to do the C compilation, jam them together into one line, and we get libtag darwin.so, so our Java can load it. And once we've done that, we end up with something like this. We now know that we have two kind of high-level platform variants. We have the Docker target, we have the fancy Mac target. Everything above the yellow line is bytecode, so it will run happily everywhere. Everything below the yellow line, we're basically dynamically picking at runtime. Like I'm on a Mac, so I'll load this variant. And once we've done all of this, we can fire up Quarkus Dev again on our Mac, and we can hit our dive side endpoint, and we can get our very important sample data back, slap ourselves on the back, and retire to this lovely looking beach scene. But then you remember, you've actually forgotten to check the Docker variant. Can we actually start our Docker service up and see if this thing still runs? So you Docker compose up, and you end up with this rather more opaque error message with a lovely big GUID in the middle. But if we go and look at the console and apply our programmer grokking skills, we discover this, which is a bit more helpful. We can't load an ARM64 SO on an ARM64 image. And I mentioned before, you have this fancy Mac, which might have sounded a bit like Apple product placement, but it's important here. All the new Macs aren't x86-64, they're ARM64 or ARM64. So when we go and look at our build script again, we can see that we're very explicitly asking Docker to build us this image for AMD64. And this is cool. It's cool that we can go to Docker and say, pretend to be a totally different CPU architecture and also Linux. But the upshot of this is that we have this shared library that won't even run on our platform. And if we jump over in this rather poorly selected choice for comment color, I hope you can read it, we can see that when we ask Quarkus to start, we're not specifying a platform. We're just saying, hey, Quarkus, go run. Which means that our app that's on the outside that's loading this shared library is ending up with an ARM64 container image because you get the default for the system you're on. So we're very explicitly building a image, we're very explicitly building the shared library for x86-64, and then we can't load it. So we need to do the same thing again, but this time we've recognized that rather than needing a native variant for macOS and Linux, we also need to add this extra access for the CPU architecture. And it's pretty straightforward in this case. We can go back to Docker and we can recognize the fact that we're passing in this platform argument, and Docker is then giving us a virtual machine for the build to run inside of for that architecture. And at the bottom, we're just calling it with ARM64 and AMD64. So we wrap up the build in a nice container, we run it for the two different CPU architectures, we pull the shared library out of them, and then we can pack it all together nicely into our jar. And things look like this in the end. We still have our nice bytecode, which hasn't had to change at all for any of this, which is great. And we have three different variants of the native library underneath. And when our Java loads, it has to dynamically pick one, like, am I on Linux, on ARM64, load this one, and so forth. And you can do fancy things with your Maven repositories to pack up the Horror API in this case so that it has different variants that you pull depending on your target platform. But in the common case, you would just get a jar that has everything in it and dynamically choose at runtime. So we fire up Docker Compose again. We get back the same set of very satisfying sample data, but now we know we can run in a Dockerized container on a Mac natively and across two different CPU architectures. And this time we can retire to a different beach, we think. But then you remember, you actually also use an Alpine Linux image for production. So we fire up Docker Compose again, we try it again, this time with a production image, and we get back another error. If anyone's paying heaps of attention, maybe the GUID is the same, but don't read too much into that. And in this case, the error in the console is a little bit more obtuse. We can see that we can't load libtail, which is the important bit. LD Linux ARM64 cannot be loaded, which is something we've had nothing to do with, right? But we can see that libtag Linux ARM64, which is our actual dependency, is trying to load it. And in this case, it has a little bit to do with C runtimes. So when you want to do any work on a Linux machine, you have to ask the kernel to do it for you. And when I mean any work, I mean anything that affects the outside world, like printing to the screen, opening a socket to connect to a web server, or reading or writing from a file. But the way that works super concretely isn't very organic. You're basically putting some magic numbers into CPU registers, like maybe you put 34 in EAX and a pointer to a string in EBX. And then you fire a soft interrupt, which kicks the system into kernel mode, which reads the magic numbers out and decides what you asked it of. This isn't great as a developer, right? So what we do in practice is use these C runtime libraries, which wrap that rather unpleasant calling convention up and give you regular functions to invoke. And there's a bunch of different variants of these. There's glibc and musl, which are kind of the main two for Linux. There's MSV CRT for Windows, and I'm sure there's all sorts of other ones that I've never even heard of. And an important property of these on Linux is that they're distribution specific. So generally on Linux, when you use a runtime library, you end up with glibc, except for Alpine. Alpine is famously very focused on providing a small, tight, opinionated Docker container, and it uses a completely different C runtime. And when we build libraries with GCC or LLVM or what have you, we implicitly take a dependency on the C runtime that's available when we build them. So our library is dependent on glibc, even though we haven't asked for it, and now it can't run in Alpine. But this one is pretty easy to fix. Essentially, all we need to do is change the surrounding container, which we see in the bottom, to use a builder image that has musl instead of glibc in it. We have a different command to install the compiler tools, obviously, but then everything after that works the same. We end up with an implicit dependency on the different runtime. And at the end, we have quite a sprawl of axes we need to worry about to make our library actually run everywhere. We have operating system by CPU architecture by C runtime. And this, I think, kind of gives you an idea of how much horror Java lets you avoid. And also, when you use a native Java library that's packed up into Maven Central nicely, you don't even notice any of this. Like, there's a lot going on underneath, and the package maintainers have done quite a bit to hide that from you. So we fire up Docker Compose again, we hit our endpoint again, and this time it works with Alpine with our production image. And we can retire to our desert island, we can commit, we can push, everything goes through CI/CD, is released happily, and we're done. The service never needs to be touched again, it's perfect. And that's it. I've been Scott. If you want to come and hassle me about any of these things, grab me while I'm walking around. Otherwise, enjoy the rest of the sessions.